This part of the lecture is entitled Polarized Neutrons, okay? So there's not much about X-ray, magnetic X-ray scattering here. But in one of the appendices, there is some information about magnetic X-ray scattering and resonant X-ray scattering, if you're interested. Yeah, so the one point, though, is that a lot of the things that you do with neutrons, especially in these low Q applications, for reflectometry, for instance, the formalisms, lots of the formalism is the same. The difference between neutron and X-rays is just how they interact with the material. They're scattering powers, if you like, okay? So just keep that in mind. A lot of this you can use for X-ray stuff, too. Okay, so again, this talk is entitled Polarized Neutrons, but it's going to include what you do with polarized neutrons, and a large fraction of which is to use the polarized neutrons to study by reflectometry or in diffraction. Again, we'll use reflectometry as an example because it's a prototype. Remember, reflectometry and diffraction, elastic scattering, are the same thing. Reflectometry occurs at relatively low angles, low wave vector transfers. Diffraction just occurs at higher angles, higher wave vector transfers. At low angles, you need to use the exact solution to the Schrodinger equation for the specular reflection. At high angles, the Born approximation or the Fourier relationship suffices, okay? But that's the only difference. It's kind of an arbitrary division, all right? So all elastic scattering, and the whole point of doing elastic scattering is to study the structure of the thing that's doing the scattering, okay? So here we go. Let's talk about this. And again, there are appendices that have the X-ray stuff in it. But we'll talk in the first part about just some fundamental ideas about what neutron polarization even is. And then in part two, the application and the study of magnetic structures for all of those, for those of you who do hard condensed matter structural studies, or maybe will sometime in the future in your careers someplace. And then there are applications, even though you may care nothing at all about using magnetic layers. You're studying biology or chemistry and have no interest whatsoever in magnetism. It turns out that if you're studying, for example, like lipid bilayers, you can use in those reflectometry problems magnetic reference layers, which are really nice if you have polarized neutron beams, because then they supply references that are, number one, totally external, as you'll see, from the biological or other film, chemical film of interest to you, that don't interact, don't cause any problems, like with hydrogen deuterium substitution that they sometimes do. And you can use that as reference. So you can use polarized beams and the fact that they scatter differently from magnetized ferromagnetic materials as your references, and not mess up the system you're really interested in studying chemically. Okay, and then there's this part, I don't know, have you had in this week anything about spin echo measurements? And measurements are very, okay, so we should touch on that, because there's a way using polarized neutrons that, typically with neutrons and do inelastic scattering, you measure energy transfers of the order of milli-electron volts. But by using polarized beams in a spin echo technique, you are able to measure microvolt energy transfers and below. And I'll just try to show you a little bit about how that's possible to do. So that's a very valuable technique that has not necessarily any bearing on, or is not related to any interest in magnetism, but it uses magnetic materials and polarized neutrons to enable you to study non-magnetic systems of interest to very high energy and actually wave vector transfer resolutions. Okay, so again, you can read this list and go through all of this, but again, we'll just sort of quickly excerpt the main points. Neutron has a spin half. It's a fermion, and that spin half is associated with an actual magnetic moment, has a nuclear magnetic moment. The neutron, it turns out that in quantum mechanics, everything is quantized. So the neutron has a magnetic moment, but it can only be two values, either pointing up in a magnetic field or pointing down in a magnetic field. There ain't anything else, okay? That's all there is. Okay, but it does have the property that when you create a beam, an ensemble of neutrons, that has not perfect polarization, it's not all spin up or spin down, it has some distribution, we can map onto this abstract idea that physicists came up with of polarization that is attributed, it's a property of the beam that has very, very useful characteristics, as I hope we'll see a little bit. Okay, now it also turns out that if you are interested in studying magnetic materials, the neutron magnetic moment interacts with atomic magnetic moments in a material, in a magnetic material, with with a power that's comparable to the neutron nucleus interaction. So that means, relatively speaking, it's pretty big. So if you're interested in studying magnetic materials that are of interest to you, then neutrons couple to that pretty strongly as it does to the typical nuclear scattering interaction. Okay. And then if you're really interested in this stuff, again, because quantum mechanics is really so hard to understand intuitively, there are some really good books. And one of the ones I found in, reading over the years, and again, somebody was asking me a question at the beginning, in between the lectures, there's so much here. Yeah, well, it took me like 30 years to learn this stuff, so don't expect that, unless you're a super genius, to know all of this stuff after these two short talks. I probably will confuse you more, but at least you'll know to go look somewhere to figure out what I'm talking about. But the one thing I did find that if you are interested in spin, if you are doing magnetism, this book by Eugen Majkrzak, it's probably out of print, but I found one once online that came from the Austin Public Library. They were getting rid of it, so I bought it for $3 or something, but it has a really good description of how spin in quantum mechanics is described, okay? Okay, so remember we had this representation of the neutron as a wave packet, but then we said, well, the components of the wave packet are plane waves. And this one plane wave is a good starting place to describe how the scattering occurs. Well, if I have a polarized neutron beam so that that's in a magnetic field, it defines a quantization axis so the neutron moment knows there's a magnetic field around it, so it knows it, oh, I got to point up or down. Then this wave function, this plane wave, is still a good representation, but we have to have a pair, two parts, a sum of two components. One that represents the energy that the spin up neutron has in the magnetic field. So if I have a magnetic field like this, neutron up has a different energy when it's aligned than when it's anti-aligned. So spin up and spin down have different k vectors. The k vector is bigger for one than for the other. So this is a representation of the neutron as it could be. It could be, again, it's almost like I'm contradicting myself. I say it can only be in one spin state or the other, yet I have to describe it by a wave function that represents both at the same time. And that's because you don't know which one it's in until you perform a measurement, until I go and project out by some polarization device and find out what state the neutron is actually in at that point of measurement. So up until that point, this wave function, not the square of it, represents all possibilities. It can be either up or down, and we don't know until we find out by measuring, okay? So anyway, let's not dwell on that too much. Again, it's a mystery of quantum mechanics, and nobody completely understands that still to this day. But some of the things that we do understand are how the neutron interacts with magnetic materials. And we remember in the first talk this morning, we talked about how the neutron interaction at low Q can be described by a refractive index n, and that it represents some nuclear potential, but the magnetic potential can be described in addition just by adding on to it either spin up or spin down, which means the moment of the neutron times the field, the magnetic induction it happens to be in, or minus that for the downspin state. So now I have a refractive index that's a little bit more complicated. It has a nuclear term and it has a magnetic term. And since there are two spin states, they can add together or they can subtract. So there's what? There's an interference now. So a neutron scatters from a magnetic material. It sees the nuclear scattering potential and it sees the magnetic scattering potential simultaneously. And depending on what spin states it's in, the spin state the neutron happens to be when it interacts, it could be a big potential, or if these two things are equal, in fact, it could be zero potential. It doesn't see anything. Okay, so here's just, the typical quantum mechanics. To measure the wave function, or to get some measurable quantity, we need to have the wave function squared, the intensity actually. So we have to, multiply these together, but in the proper quantum mechanical way. And you can look at this and study this. But again, we don't want to go into a lot of detail here. We just simply don't have the time. But remember how we solved that one-dimensional Schrodinger equation for specular reflection for a neutron that wasn't polarized? Well, the whole solution scheme is the same, but now, unfortunately, it gets a little bit more complicated. If I have a neutron that's spin up and it scatters from a magnetic material, well, many things can happen. It can scatter and interact with the nuclear and magnetic potential and go away in the same spin state it came in with, or not. It could actually get flipped over. So we have to take that possibility into account. So what this equation, this one Schrodinger equation, represents that possibility by including in a term for the potential, a potential that represents the situation where you have scattering and it goes from spin up, which is represented by 1, to spin down by 2, and vice versa, down to up. So it turns out now you have a pair of simultaneous second-order linear equations to solve. But again, the procedure for this is the same like we talked about earlier. The potential is more complicated. And again, this is where Merzbacher's book is really useful to see how Wolfgang Pauli actually first represented the neutron spin as a spinner, as these 2x2 component matrices, to get the total potential out. And again, we can't possibly study this in detail now, but it's there. You can go look this up and study it if you need to. But at the end of the day, the bottom line is that to relate the transmitted and incident beams to the reflected components, we now, instead of a 2x2 matrix, we have a 4x4 matrix, which includes the possibilities of spin flip and non-spin flip processes for the neutron in interacting with that material. So again, it's a bit more complicated, but what's the advantage of all this? As you'll find, as I hope we see, is that the benefit that we get from this, the added complexity means that the neutrons are sensitive not just to nuclear scattering density distributions, but to the magnitude of the magnetic scattering density distribution throughout the material that you're scattering from. And if you use a polarized beam, not only do you know the magnitudes of the moments, but the directions in which they point in space. So you get the full vector magnetization depth profile in addition to the nuclear scattering density depth profile by using polarized beams. One thing also to remember is that for neutrons, the neutron-nucleus interaction is confined to a region of space that's a tiny, tiny, tiny fraction of an angstrom, a Fermi unit of length. So we can treat the neutron-nucleus interaction for all practical purposes as if the neutron scattering power were concentrated at a point in space. The magnetic scattering arises from the interaction of the neutron with the unpaired electrons distributed throughout the unit cell of a material. So again, if you extend something in reciprocal space, okay, or in real space, you also have a corresponding effect in reciprocal space, so that means that it isn't as though it were coming from a point any longer, that the Somebody asked me a question. Okay. I'm sorry. Okay. This is so-called form factor. It means that if you look at the distribution of the magnetic unpaired electrons that are giving rise to the magnetic scattering, they're coming distributed out in space. Okay? Okay, I'll just talk over this. But this distribution means that the scattering power is a function of Q now. We can't just assume that they're at point locations, all right? And that means that we have to worry if we go to higher Qs that the scattering power associated with that particular magnetic atomic moment is going to be less at higher Qs than it is at lower Qs. But people work this into the calculations, but just so you make sure you're aware of that. Okay, so remember I said spin up, spin down. That's the only two possibilities for the neutron spin, magnetic moment. But if I have a beam, I have the possibility of a beam having not all 100% of the neutrons in that beam being spin up or spin down, but maybe 85% are up and 15% are down. Well, I can create this abstract idea of a polarization as defined by the population of spin up, the difference between spin up and spin down divided by the sum, by the total number of neutrons in the beam. And if these are equal, if n plus and n minus are the same, 50 up and 50 down, this polarization in the z direction along the magnetic field is 0. If it's 0, it means the beam is totally unpolarized. We go back to the first lecture this morning, and we're done. Okay, but if I have a device, as we'll talk about in a minute, that can create a non-zero polarization, then we can actually do some experiments that may take advantage of that. Okay, so again, going through all this stuff is really complicated and really pretty non-intuitive, but it's just to point out that you can think of a top in classical mechanics as having, a moment of inertia. It can have an angular momentum. But you can also think of the beam, this ensemble of neutrons, characterized by some polarization vector as well, okay? And there are different ways to describe this, and it turns out that the real difference between spin up and spin down is the refractive index. Remember, the K vector in the field for spin down is different than for spin up. So you get, if you have a if you have a beam that does not have a perfect polarization of 1, but has some non-unit value, then this polarization vector relative to the applied quantization field, the magnetic field, is tilted. And as it propagates through space, because the K vectors have different values, you get precession. So this abstract quantity that we describe as polarization rotates in a conical fashion as it progresses through a magnetic field with that particular polarization. And you can construct various devices just with macroscopic magnetic fields that let you take a polarization where the P is along, let's say, prepared in a region of space where it's perfectly polarized along the z direction, and then enter abruptly into a region of field where the B field points orthogonal to what it was outside, and that polarization vector, because of the difference in K plus and K minus, will rotate. And so you can take a beam that has a polarization that's up and rotate it till it's down or anywhere else that you want. And if you come out with it only partially rotated and go back into the original field along the z-axis, you'll get that precession I was talking about. So the beam, the polarization of the beam, can be manipulated in very simple ways. We just take a flat solenoidal coil and have it pass from one quantization axis to an orthogonal one across a distance of only a few microns, and it finds it can't react fast enough, it can't precess or Larmor precess to adapt, and it just comes out in a different quantization axis state. In a region of space, rather, with a different quantization axis, and begins to rotate or precess. So here's a typical instrument. This is the reflectometer at NIST. And this actual picture is represented by the schematic at top. The beam comes in from a cold source down a guide tube, is monochromated here with pyrolytic graphite, and then there's a pair of slits that define the beam. Actually, I should have shown this in the first talk. There's how you make a reflectometer, okay? You monochromate the beam to get one narrow wavelength bandwidth, basically monochromatic with delta lambda over lambda of the order of 1%. And then have it reflect from a sample with a very well-defined angular divergence that is created by this pair of slits a distance apart. Okay, now at a pulse source, you do an experiment at SNS, you have pulses that have a wide bandwidth of wavelengths, and you separate those out by time of flight. But the principle is exactly the same. This is just showing you one component at a time at a monochromatic source, a monochromatic steady state source. Now, to make a polarized beam, you put a polarizing device in here, which we'll talk about in a minute, and then you have a flat coil flipper, a solenoid, that allows you, if the field is in this direction, to have a field pointing like this, orthogonal to it, so you can rotate the polarization around and have either spin up or spin down incident on your sample. And then you repeat this polarizing device and flipping device in the back end, so you can see whether the neutron that was scattered by the sample got flipped or not flipped after the interaction. So this enables you to do the full polarization analysis in studying the scattering from a sample. So how do we do this polarization thing? Okay, remember that the nuclear and the magnetic scattering potentials are summed together. So for one spin state, both nuclear potentials always look the same, but because the neutrons, the nuclear magnetic moments, if they exist at all, are randomly oriented, so you don't get any polarization by that interaction. So it just looks like a scalar scattering potential. But the magnetic atomic moments are different if they're aligned in a ferromagnetic material, so that in one case, the spin-up neutrons may see nuclear plus magnetic potential, and the minus neutrons in this unpolarized beam incident may see rho nuclear and rho minus, the difference. And if you pick the magnetic and nuclear scattering lengths and densities to be just equal to one another by proper selection of the materials, you can make this zero, so that if a beam comes in like this, one spin state sees that and reflects very strongly below this critical angle with unit reflectivity, in fact, whereas the other spin state sees the difference in the two, and it doesn't see anything. It looks like empty space, and it goes straight through. So the reflected beam is polarized almost perfectly spin up. The transmitted beam is polarized perfectly spin down. So that's how you make a polarizer, just with a thin ferromagnetic film, for example. There are more complicated devices that use multiple layers to extend, called a super mirror, that extend this region of reflection to higher angles. But in principle, it works the same way. Okay, so what are some applications now? We know how to rotate the beam, we know how polarization, we know how to polarize now. So suppose I have a layered material. This could be a crystal at high angles, or it could be at low Q, a layered film with large length scales of tens of angstroms or nanometers. But suppose that this lamellar structure has atomic planes in which the nuclear scattering density is the same, indicated by this reddish color, and then it changes here in another set of planes to this bluish color, different value. But in this reddish color, there also exist atomic magnetic moments. Now, these atomic magnetic moments may, for example, in one atomic sheet, all be lined up ferromagnetically parallel to one another with a net magnetization. And then the next layer may go over, and they may be pointing in this direction, and then back again in this direction. Well, by taking advantage of the fact that the nuclear and magnetic potentials interfere, it turns out they do so only in the non-spin flip scattering. And when you have an event where a neutron comes in one spin state and reflects in another, it turns out that that's proportional only to the magnetic scattering density. So these are the selection rules. This is what turns out when you work out through all the mathematics. So these two very simple reflection selection rules are immensely powerful. Why? Well, it's because what I alluded to before. If I have a net magnetization in the plane that's pointing in this along this 45-degree angle, the projection of the magnetization onto the vertical axis gives rise only to non-spin flip magnetic scattering, and it interferes with the nuclear part. On the other hand, the projection of that net magnetization onto the horizontal plane scatters neutrons that are only spin flip without any interaction with the nuclear part. So if I measure all four of these reflectivities or scattering cross sections, okay, with the device we saw a few slides back, that polarized beam reflectometer, if I measure plus to plus scattering, minus to minus, plus to minus, and minus to plus, then we get out not only the nuclear and magnetic magnitude depth profiles as a function of along the z-axis, but I get out also from this the projections on the horizontal and vertical axis, which means when I add the two components together, I know what direction the magnetization is pointing in. So I get the vectorial magnetization depth profile. This is extremely powerful. This is how we know almost everything we know about the microscopic magnetic architecture of materials comes from neutron scattering in this way. Okay? There are other selection rules besides those two main ones. You can sometimes put the magnetization axis, the B field, at the sample position along the Q vector. And if you do that, you are sensitive also to chirality, to rotations of the spin in the plane. So there are other selection rules that you can study and look up, but again, at the end of the day, the thing is that you can configure the experiment in such a way that you get all of the magnetic information and orientation about the sample out. And one thing I've neglected to say was that the neutron only scatters magnetically from components of the spin that are perpendicular to Q. If I have a magnetic moment along Q, zero scattering. But that fact that you don't see anything tells you it's along Q, if you know there are magnetic moments there. So here are just some quick examples. Here's a ferromagnetic system. Everything's pointing up perpendicular to the z-axis along this applied magnetic field. And you see that you get scattering if it turns out that the nuclear and magnetic scattering amplitudes just happen to be, very close to one another. You get, for one spin state, very strong magnetic scattering at this periodicity, okay, showing you that there is a magnetic moment pointing in the same direction from one layer to the next and so on down along Z. And the other scattering cross-section will look just like this without any magnetic component. If you have an antiferromagnetic structure, then things start to get really interesting. And here, there is a chemical periodicity that's the same as here, but now, because the spin goes to the right and to the left and to the right and to the left, actually one unit cell is double the length of the chemical unit cell, where the nuclear scattering is appearing. So now you get a big magnetic scattering peak that occurs because of the reciprocal relationship between real and scattering space, you get a peak that represents the magnetic scattering, and it's all spin flip scattering that occurs at half the Q value that the nuclear scattering peak that occurs at this periodicity. Okay? So again, yes? Okay, why, the question you're asking is why, what is?
The reflectivity plot.
Yes?
Why isn't that red form lined up with the top black line?
Why is the vertical angle mode showing a reflectivity of 1?
Over here?
The critical angle.
There's no total external
Oh, no. So, okay, the reason, no, this is an excellent question. So you're asking why you don't see total reflection here. And the reason is that over that length scale, the up and the down cancel one another out. Okay, if they're all lined up, then you get a strong signal. And there's in fact a difference between the two critical angles, but there's still a magnetic contribution to that. That's how the polarizer works. But here, because you're plus and minus over this length scale, you don't, at low Q, at the critical angle region, they just sum together. You don't have that spatial resolution at that low Q to distinguish the different directions that they're in. They just sum to zero. The net scattering power is zero. And furthermore, you have to remember that there's no nuclear scattering there because that magnetic signal is only coming from the spin flip scattering that does not involve any of the nuclear potential. If it did, then there would still be a critical angle here because the nuclear part was contributing there. Okay? All right. So here you could, yeah, you want me to go back to that slide?
So you're going to show helical system next slide?
Yes. Okay. That was easy. Now it'll get difficult. Okay, so here is a canted system where you have this oscillating antiferromagnetic to the right, to the left, to the right, to the left. But now there is some component that's pulled up along the H. So there's the component that's vertical that interferes with the nuclear part is the same here, 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 here. So now, if you look at the non-spin flip scattering, which involves the interference of the nuclear and the magnetic parts, you get another peak here at the nuclear cell position. Okay, so that's spin up, spin down. They both scatter, one more strongly than the other, but they're both there. But again, the projections of this structure on the horizontal plane here give rise only to spin flip scattering. It's purely magnetic, and again, it has still the characteristic double unit cell. So you can stare at these things and think about it a little bit. And then here's a helical structure that wraps around like this. And that gives rise, again, to this structure. Now, the one thing, this thing, if you analyze this, the only way that this is consistent with the data are consistent is with this particular structure. This is the only thing that will fit the structure. And here, the phase ambiguity is not serious because it's presumed that when you fit these things, you're going into this knowing the nuclear structure. So that in itself is the reference. That's your constraint that fixes the phase, okay? You may not know that in some cases, but then it's better to do some other scattering experiment with X-rays or non-polarized beams to find out, first of all, what the nuclear structure is, and then you have that to use in analyzing the magnetic structure, which you might not know a priori. Okay, the one thing I'm just going to point out here is that this is, again, for the situation where you have the beam polarized along in plane, perpendicular to the z direction. But if you were to put the magnetic field, let's say the structure, you put it in a small magnetic field, just enough to keep the beam polarized along that quantization axis, and it didn't disrupt the magnetic structure, if you put the field along this direction and did the scattering, you would be able to tell whether that was a right or left-handed spiral, because plus minus and minus plus would be different. Okay? But that's one of the other selection rules, so we don't have time to actually study in any detail. So one of the things that's really important is that just like we talked about this morning, the first talk about making samples that are good to study, like these biological samples, really, very simple systems, simple lipid bilayers, simple protein, single protein going in. You can make by molecular beam epitaxy or other systems where you can actually do single atomic plane at a time depositions so that you could create really, really beautiful single crystalline samples artificially that are layered. So this is really interesting. Now, you can take a magnetic layer, let's say this is a ferromagnetic slab of 3 atomic planes, and there's another one up here, and you can interleave between these 2 layers, these 2 sets of atomic planes, some other material that's non-magnetic, different type of magnetics, semiconducting, superconducting, semiconducting, insulating, metallic, whatever you want. And for example, you could study what the magnetic interaction between this slab is with respect to that slab. But you can do it in a systematic, controlled way, using polarized neutron scattering to study that system that you construct. And it turns out that if you look at the low and high Q structures, high diffraction angles and low Q, you can get not only what this magnetization is in the magnetic layers, but if this is so, suppose as it is in the case of chromium, an oscillating spin density wave, by looking at the higher Q data, you can see with atomic resolution, because you go to high enough Q around some Bragg point associated with the atomic plane spacing within the layers, the other length scale. There's two length scales, the atomic plane length scale, and then there's the superlattice length scale of the layers. And you can get, in fact, the detailed structure of how the chromiums oscillate and actually get twisted between the iron layers. So lots and lots of studies like this have been done and give you exquisite, detailed information about those magnetic architectures. Here's another case where you can intersperse magnetic layers with atomic plane, whose atomic planes have net magnetizations, and intersperse it with other materials that cause the interaction between these planes not only to be different, but to be not at all. You can get to a situation where it's completely uncorrelated and there's just a broad peak, or where it's very well-defined correlations that give you the exact structure and the results of that that are deduced from those particular positions and spacings of the peaks. So not only do we get information about the local magnetic structure, but we get information about how those local magnetic structures interact with other local magnetic structures a distance away across these intervening layers. So this tells us about interlayer correlations, interlayer exchange coupling, for example. So again, neutron and scattering in general tell you about these correlation relationships. So maybe you remember many years ago, now, almost 10 years ago, Albert Fert and Peter Grunberg won the Nobel Prize for the giant magnetoresistance effect. So for those of you who don't know what that is, it turns out that if you have layered systems that have ferromagnetic atomic planes, let's say 5, like the fingers of my hand, interspersed across a non-magnetic layer or weakly magnetic layer, and then there's another ferromagnetic layer. When these two ferromagnetic layers are aligned, so all the magnetizations of the atomic planes are pointing in the same direction, the resistance is relatively low. But if you could somehow rotate the second layer so that it's still ferromagnetic, but now it's pointing in the opposite direction to that layer, the resistance goes way up. And that's how all our read heads work in all your computers now. And it's so important that they got the Nobel Prize for this. But what is this mechanism that causes you to be able to have this as opposed to that? Well, the mechanism for how that happens was discovered, in fact, by neutron scattering and before giant magnetoresistance was discovered. So if you look back, there's a lot of work that was done on rare earth magnetic layers. So you could take gadolinium, and make, by molecular beam epitaxy, layers of hexagonal close packed structures that had atomic planes that were all ferromagnetically aligned, and interspersed between that and another set of these gadolinium magnetic moment planes, non-magnetic yttrium. And you could study this, like I was mentioning a few slides back, by neutron scattering. And it turns out, if you take a system like gadolinium yttrium, so you have the gadolinium, again, all ferromagnetic, all pointing up in one direction, and if I change the number of atomic planes of yttrium between this gadolinium slab of, let's say, 10 atomic planes and this one, you'll get all the spins to be up. But if I then make another system where the yttrium layer thickness is different, I find that they all go almost anti-ferromagnetic in this canted state. And no, not canted state, but spin flop state. And it turns out that the explanation for this is the long range, RKKY interaction, long range indirect exchange. It oscillates. It depends on how far apart those ferromagnetic layers are. And all of this was verified from the neutron scattering data that showed in a systematic way by making many different superlattice samples with different yttrium layer thicknesses that this oscillated with the same period as predicted for this RKKY interaction. So that's how the giant magnetoresistance works. Again, and the understanding the detailed nature of this mechanism is discovered by neutron scattering. Okay, now I mentioned also that if you have ferromagnetic layers, they may be useful to you, even though if you're not interested in magnetism. And the biologists like to study these lipid bilayer systems with embedded transmembrane and other types of proteins in them. But they like to be sure and have the phase information, so you could change this from H2O to D2O and do experiments like many people do with changing the phase contrast in the water. But sometimes the water exchanges differently with components of the system, and it causes things to become really complicated and uncertain. But if you want to get phase information out, you can make a reference layer, magnetic layer, that's buried beneath the gold layer, which chemically isolates the system of interest from this reference. And so you can use a polarized neutron beam, a magnetic layer, make by effect then two composite systems, the unknown, which stays the same, and the magnetic layer, which is different for spin up and spin down if it's a ferromagnetic saturated layer, and get two sets of reflectivity data. So now you do spin up, spin down with a polarized beam, get two sets of data, and extract from that the real part of the reflection amplitude that corresponds only to the only to the biological film of interest. So here's an external reference that doesn't mess up the system you're interested in. And here are a bunch of examples how that works. And there's one more. So here's a beam. This particular biological macromolecule is studied with this different spin states interacting with iron nickel alloy called permalloy. And the result of this simultaneous analysis gives you the details of where that thing sits. Okay, so in the last, I think I have 10 more minutes left, Brian, is that right? Okay, good. So now let's just talk a little bit about what you, again, don't be afraid to ask more questions. Anybody have any questions up to this point? Good. Yes?
So the chemical system you showed.
Yes.
Can you please go back to that?
Sure. Okay.
So at about Q.8,
Yes.
inverse diameter, you have no reflectivity at all. Is it because of the rotating spin now have exactly opposite direction? Or is it
You're thinking too hard. This is the non-intuitive part of this. It just happens that for that particular structure, if you go and calculate that using, you make a model of this, and these are exactly calculated from that model. That's where a destructive interference occurs. I can't, remember, the relationship between reciprocal space and real space is such that a localized thing in the real space is distributed over the whole scattering space, and vice versa, right? So it's the Fourier transform relationship. So it's very hard to describe one feature in real space with one particular place in reciprocal space. Okay, that information is spread out. But it's still possible sometimes to see certain features that, that's not a totally rigorous statement. It just means that it's, in general, it's hard to determine exactly what caused that particular interference minima. Okay?
could it be the long
No, it very well may. Because in fact, I mean, you're observing, in fact, you are being very observant to note that that is at the period of the helix, right? Yeah. So there's something to do with that, but the exact nature of which you actually have to convince yourself by doing those calculations and then deducing that, oh, that must be why it is that. And sometimes you can do that. But in general, what I would say is that this whole curve, all of these curves correspond to that structure, not any one particular place. Sure, you're right. You can say, well, this peak maximum occurs here because that's the period of that, and so on. But really detailed information, you have to say, comes from the whole scattering space. Okay? Oh, I went the wrong way. Oh, no, I did. Sorry. Okay. So we're going to go now and talk a little bit about how we can take advantage of using that spin and the polarization to actually measure very tiny changes in energy and in momentum transfer. And that comes about, again, because of the difference between K plus and K minus, enabling us to describe a beam as having some polarization. So I just wanted to go back to this one. No, let's go over here. Sorry. One more. So this polarization now for the beam, we can take advantage of that and use it when we create a beam that's perfectly polarizing in one direction and then rotate it purposely into a plane that's perpendicular to the quantization or magnetic field axis so that the polarization of the beam precesses as it propagates through space. Okay? So let's go now to this. Almost there. Okay. So imagine, if you will now, that you have a polarization that's, you use one of those supermirror polarizers to polarize the beam along one axis. And then you take a magnetic field region confined to this space in this rectangular volume that has inside of that box a magnetic field that's pointing in an orthogonal direction out of the plane of the screen. So when that polarization and the beam go through that box, if you make the magnetic field magnitude just right, you can make the beam polarization go from up to exactly orthogonal, so that the beam exits with a totally undefined polarization insofar as spin up and spin down is concerned, but the p vector is still pointing along this direction now, orthogonal to pi as it exits. Then if this is an empty field, there's no field in this space, and then it enters a field region again with the polarization axis perpendicular. If it comes in lying along this axis, let's call it the x-axis or whatever, as it propagates across this volume in this field at right angles, it will precess. And after it comes out, it may be pointing here or here, somewhere in the plane, but then if I rotate it back in such a way, with the right field magnitude, I can get it to come back up again. Or not. I can do anything I want with this setup. So I can take it and rotate it down, precess it around, have it come up like this, like this, like that, wherever we want it to come up. But let's do the simple case where we just take the beam and we rotate it so that it's perpendicular to this new field direction and it's precessing in a flat plane like this as it propagates through that region. If I do that and I have a beam go through a length L of this region, it may turn out that if I start like this, I go through and I come back out exactly like that. Okay, for that field strength. But suppose a sample is in front of the beam and it causes the beam to deviate in angles so that it doesn't go this way and come out exactly like this, but it heads out in a different direction. Now this direction, it's still in the same field, it's still precessing the same way, but what do you notice about the path length? Is it longer? Yes. So when I go this way, I'm not going to come out exactly like this, unless by accident, but I'm going to come out at some other angle. So what does this tell you? If I had a way of measuring the polarization at the end here, I know it corresponds to this length L. But if I come out with a measurement that says the polarization is not what it should have been here, it must have gone in a different direction. And it turns out that you're counting these so-called Larmor periods with extreme accuracy if that field is high. It does a lot of rotations. So just a tiny change in the length of path length means that you get a big change in the polarization coming out. So this is an extremely sensitive way to measure different field lengths, okay? So how is this actually, okay, you know, there are other ways to measure lengths of magnetic fields than this, but what's really important is that we can apply this to studying how things are scattered by a sample, not only elastically, but inelastically. So let's look at this. And this is the end of the lecture, basically. So if you can just grasp this point, this is the most important part. If you start out with all the polarizations along this direction in the vertical, and I have them go through a region where the B field now is, instead of up and down, is out of the plane of the paper, then as we've been talking, the neutrons will all precess in the same direction, but this direction is longer, the red and the blue directions are longer than the yellow directions. So when those neutrons precess through that region of magnetic field, they'll come out pointing in different directions because they all had different path lengths, okay? Now here's the really ingenious thing. This is the neutron spin echo technique that Hahn applied to molecular beams and Ferromagnetic applied to neutron scattering many years ago, and it's become an extremely valuable research instrument type of method for studying such small energy and angle changes. If I take a second field region, pretend there's no sample here, that's just the position of sample, there's nothing there. If I configure a second precession region such that the field, instead of pointing out of the paper, is reversed, then these neutrons take the same path lengths in the second region. The red goes red, the blue goes blue, the yellow goes yellow. But instead of precessing in this clockwise direction, when they come to the reverse field, they precess in the counterclockwise position. And lo and behold, when they all come out of that region, back in the original field direction, they're all lined up. And that's called spin echo. Okay? That's beautiful, it's great, but it's useless just by itself. What you want to do is to mess it up. So you mess it up by putting a sample in here. And now you destroy that symmetry. And if you put a sample in this beam, such that it changes the scattering angles so that the blue, I'm just showing the central ray, so the yellow one that was originally going across here now goes either up or down, it's going to come out not back lined up again. So the polarization that you measure at the end is not going to be unity, it's going to be some lower number. And that tells you the degree to which that polarization changes is a very, very accurate measure of how much that path length changed. Now, the path length can change by another mechanism. This path length changed because the sample just elastically scattered it up or down. But suppose all the neutrons go through the same path without any deviation in angle, but the interaction with the sample was inelastic, so the neutron coming in with this velocity scatters from the sample and then it goes out a lot slower. Then it's in the field a longer time, it precesses more, and you also get a change in polarization. Okay, you get it? So you can either change the path and get a measurement of wave vector transfer, very small angular deviation, or you can change the energy of the neutron and get a very accurate measure of how the energy is changed. Okay? So again, remember, this is, I keep saying it's accurate. It's accurate because if I make these field strengths long, big enough, there are many, many, many precessions going through. So all you have to do, it's modulo 1 full 2 pi precession. So I make a lot of precessions. If I'm not exactly right coming out at the end, the polarization is going to be way off in that 2 pi possible circle. So it becomes extremely accurate. You can measure microvolts. You can measure, tiny, tiny fractions of a second of arc change. Okay? So I think this is just, there's some of the mathematics in there to show you how to do this. Okay? Which we don't have time to talk. There's an actual use of this to figure out a structure. And there's some current examples of spin echo spectrometers that exist. And I think that's it. Great. Okay. Yeah, I'll hang out here. Unfortunately, I won't be here for lunch if you have questions, but email me, please, okay?